Okay, this is going to be part 2 of our discussion. Somebody pointed out, Abby, my great human spell checker, excellent, she pointed out 2 mistakes. See, I'm from a town in the United States called Wall Township. Wall Township. So when I spell the Dutch name, Wall, this should be 2 A's, okay? Yes? And then this one, dynamic, okay? Aliens have landed on the roof, but they're very little, and our roof is very thick. It's alien proof, so that noise you hear, we're still safe, okay? Understood? Enzo's looking at me very seriously, like there really might be aliens up there. Excellent. Okay, but you can't fight them because you're on the DL. Is that like an American thing? The DL? Do Americans know what DL means? The DL? What is it?
Like down low.
No. Well, yes, down low, but that's not what I'm talking about. The disabled list in baseball, you're on the DL, 15-day disabled list. You have no idea what I'm talking about, right? In baseball?
Exactly, baseball.
Yeah, it's an American thing. DL, be on the DL. Okay, so let's begin. Let's begin with sublimation. I think we left off at number 4, maybe something. Anyway, what's sublimation? Let's talk a little bit about sublimation. Now, sublimation is very interesting in the book. Okay? Yes, Yusef.
To change from a solid form to a vapor form and without passing through liquid form.
Okay. Sublimation is our resident Egyptian, excellent. God bless all Egyptians. And he said that it is the transition between a solid and gas without a liquid state, excellent. And the opposite of sublimation is the deposition, excellent. So read the definition in the book for sublimation. Now, as you're doing that, we'll have a little bit of a talk. When we talked about sublimation of water, for instance, we said, okay, sublimation for water is at low pressures, like less than 600 pascals, as opposed to 101 kilopascals. And then also, is that still on? Everything's fine?
Yeah.
Can you be my videographer? We imported a videographer straight from Santander in northern Spain. He's a world-renowned videographer. We simply call him Pablo. Pablo. If you go under videography and you look up the word Pablo, you'll see a picture of, he gets $1,000 an hour, we're paying him. So the video production is very expensive here. So if it looks good, it's simply one word, and that's Pablo. Okay. So, water sublimes at really cold temperatures and low pressure, right? Didn't we say that? But then let's look at the definition in the book. What does it say? Anybody? Read that to me loudly, and I will interpret what you read. Anybody? Pranita?
The change of a substance from a solid to a vapor.
The change of a substance from a solid to a vapor
Without passing through the liquid state.
without passing through a liquid state. That's in the book? That's what it says?
Yes.
Really? What else does it say in the book? Doesn't
It
it?
says some
In the bold type print at the end of the middle paragraph, what does it say?
Yeah, it
Sublimation
says,
occurs,
Wait, hold it. Enzo?
sublimation occurs in solids with vapor pressure that exceed atmospheric pressure at or near room temperature.
Yeah. So now it's a little confusing because if sublimation occurs that changes a solid into a gas, finish the sentence for me?
So to a gas without passing through the liquid state.
Without passing through the liquid state, but in what conditions?
That exceeds
Where the vapor pressure for the solid exceeds the vapor pressure for
atmospheric pressure.
exceeds the atmospheric pressure. So it happens when the vapor pressure of the solid exceeds that of the atmosphere, right, at room temperature. So that's a little bit contradictory, isn't it? Yes? Because what did we say? We said that sublimation was solid to a gas. That's what sublimation is, right? Yes? But it also said, relative to the triple point diagram, look at your triple point diagram in section 4. At home, if you look, find a triple point for water.
It's in section 13.
It's in section 4, chapter 13.
Oh, sorry.
Yeah, so it's there. You got it. You're open to it, Enzo. But now look at the interface between solid and gas. Where is it? Isn't it low pressure? Not atmospheric pressure. Isn't it low pressure, like almost zero pressure, and less than 273 Kelvin or less than 0 degree? So that's not room temperature. I mean, what kind of room does this guy live in who wrote that book, right? So what's the answer? Well, it says this. It says this, that if I have laundry outside, all right, in the winter. Anybody ever live in cold climates? All right, thank God, okay. So I prefer cold climates. I'm from a coldish climate, not cold, I say coldish. And I didn't realize how much I enjoy it until I came to Abu Dhabi. Abu Dhabi is not a cold climate. It's a hot climate, and I don't like it. I like it in the winter here, but in the summer, nah. So what it says is, you put your laundry out in the winter and it freezes, right? And then it gets sunny, but it's really cold, okay? So that sun, when it hits the solid, because the sun is intense. Let me digress for just a moment, okay? May I digress? You know, like last summer when I came here in August, it said 125 degrees. That's really hot, wouldn't you say? You know why that is amazing? Because that temperature is not in the sun, that's in the shade. When you give a temperature like a news broadcast or a weather report or on the web weather forecast or temperature, that's always shade temperatures. It's not in the sun. In the sun will far exceed that temperature. Clear? It can get really, really hot in the sun. We're talking much greater than 125 degrees. So, in an Arctic climate, let's say in New Jersey, where I come from, okay, it can get down to 0 degrees Celsius. 0 degrees Fahrenheit, so negative 20 degrees Celsius, right? It can get down that cold in the winter. But it's brilliant sunshine. So you go to the back of my house, and I sit back there and I read a book with just a t-shirt on. My house is white, and by my back door, it comes at an angle. It comes like this. And I sit right here on the steps, on a porch. And it's very warm out there in the winter. I have southern exposure. I'm outside. It's negative 20 Celsius, and I can sit out there with a t-shirt. Because the sun is reflected off the house, and it creates this little bubble of really warm air. Well, similar with if you put t-shirts out, they will be exposed to this intense sunlight. So you're going to take the solid ice, expose it to this intense sunshine, and create this rather intense vapor pressure. And this intense vapor pressure created by the sun on the clothing will create the vapor pressure that exceeds or equals the atmospheric pressure. So ice will sublime in really cold environments where it's sunny out. You get how it works? Yes? When you talk about sublimation in the triple point diagram, people were very confused about that last class. Those are laboratory protected conditions. You took the sun out of the equation. And those are the conditions that those experiments took place. You get it? And then you plot all the information using a computer or doing it longhand, and you get those curves on a triple point diagram. But make no mistake, water on Earth can sublime at room temperatures, provided that the conditions are, the atmospheric and environmental conditions are correct. Do you get it? Do you understand? So people were looking at that sentence and saying, wait a second, this makes no sense. I thought that you need conditions, according to the triple point diagram, where the interface for sublimation is low temperature and low pressure. Not true, is it? Those are conditions that have to exist in the laboratory, but sublimation can occur at other conditions, provided that everything is there, like the sun, for instance, and it's really cold. It's got to be really cold out. Clear? It's not going to sublime if it's near freezing, if it's near the melting point. It's not going to sublime because then it'll heat up a little bit and you'll go through the liquid phase. But if it's really cold outside, really cold, now will some of the water melt? Yes, it's all, this isn't perfect, but I needed to go through that explanation. Is that good? Do you understand? Make sense? And the reason I know this is not because I'm a chemistry teacher. It's because I'm a human who puts his clothes out. When I was a kid, my mother, we didn't have a dryer. I remember when we got a dryer, it was amazing. We got a dryer. We didn't have a dryer. How many people don't have dryers? Raise your hand here. Yeah, here it's, yeah. But we lived in a cold environment where it was hot and muggy, nothing dried, and in the winter it was really cold, and it took forever to dry, and it would get mildew. My mother would have to rewash everything. If it rained for 3 or 4 days, we'd have stuff all over the living room and cords, and it was a nightmare. And my father finally said, we've had enough, let's get a dryer. But I grew up without a dryer. I'm starting to sound like my mother when I was a kid. Yeah, it's kind of weird, huh? But, I remember distinctly my mother saying, go out and fold the laundry. And it was an incredible cold day. And I'm like, Mom, how can the clothes dry? It's 0 degrees Fahrenheit outside, which is really cold. Give me that temperature in Celsius, 0 degrees Fahrenheit. Somebody look it up. Somebody use their phone, do a conversion. I want to know what that means in Celsius. Because when I was a kid, that was common. 0 degrees Fahrenheit was very common where I lived. Very common. You don't hit those temperatures anymore, but it was common when I was a kid. So she'd say, go out and fold the laundry. Tommy, she called me. Go out and fold the laundry. I'd say, Mom, how can it dry? I mean, it's cold outside. She said, they're dry, trust me. Because it was windy and really cold, and I'd go out the laundry, and it was nice, and the laundry was really cold, but it was fresh, perfectly dry, smelled like, perfect. You couldn't wait to get in and just put the clothes on, I mean, it was brilliant, 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 brilliant. But and it was morning, so they were up, they were on the line yesterday, and overnight they were up, and it's windy. What does wind do? It lowers the pressure. So you had all these weird conditions when I was a kid, and I'd go out and I remember, and my mother wasn't a chemistry teacher. She took college chemistry in 1935. Weird, huh? But learned the same thing as we're learning now. Can you imagine? And cool? Enough said about sublimation. Are we over it? So what's the temperature? What's 0 degrees Fahrenheit?
Negative 17.7.
So I was close. Negative 20. Is that a little scary? I was a little close? It's a little scary. Okay, negative 17, negative 18.
Yeah.
Celsius, okay, cool. All right, what's next? 6, vaporization. Fabiana, weren't you talking to me something about that? Let's nail that down, because this is a little weird. I'm not even sure if it's in the book. Tell me if it's in the book.
Yeah.
This is contrary to many things that people understand this to be. Now, there's a difference, believe it or not, between evaporation and boiling and vaporization. Fabiana, can you just read that to us? What do you got there, girl?
So
This is a report. We're a reporter on the streets, did some research. Fabiana, and give us your latest research. Carry on. Go.
So the conversion of a liquid to a gas or vapor.
So this is the conversion of a liquid to a gas, otherwise known as a vapor. Carry on.
So that's it. That's what it says.
But what was all this thing about evaporation is?
It said that there were 2 types of vaporization.
There's 2 types of vaporization. There's evaporation,
And boiling point.
which occurs at the surface of the liquid, below 100 degrees Celsius. Alec, you all right with that? You look a little confused. You okay? You're okay? Excellent. So there is a evaporation which occurs on the surface of the water and occurs below boiling point, correct? Yes, and then what's next?
Apparently, boiling point is also a type of.
Boiling point is also a type of vaporization. And that occurs where?
Well, it's the temperature at which vapor pressure of the liquid
Vapor pressure of the liquid
equal to the external
equals the
pressure.
external pressure, called atmospheric pressure, or under a bell jar or some kind of other external pressure. But boiling occurs anywhere in the liquid, right? Yeah, we went over that in the video. We went over that in the last video. That would be good to look at. It's kind of cool the way I did it, I think. Yes? All right. So vaporization. Now, what is the vaporization? How much does it take to change? How many calories does it take to change 1 kilogram of water from liquid 100 degrees to gas or vapor at 100 degrees? How many calories?
1 calorie. Well, 1 kilogram of.
1 kilogram. How many calories does it take? It takes 540 kilocalories to change 1 kilogram of water at 100 degrees Celsius to 100 degrees Celsius gas. Now, so is the kinetic energy increasing? This is a different class that I asked it for melting, so this will be an interesting answer. Is that an increase in kinetic energy at 540 kilocalories?
Yes, should be.
Is it increasing the kinetic energy? How many people say yes? Raise their hand. You have to vote. This is not a democracy. We're voting,
But we're not in practice.
but you're not a democracy. How many people say it increases kinetic energy? Raise your hand. Raise your hand.
Are you raising your hand or like?
I'm just demonstrating how to raise your hand. Okay? And how many people say it's not an increase of kinetic energy, but have an alternate answer? Raise your hand.
I don't have an alternate answer.
Oh my goodness. All right, so you don't think it's an increase in kinetic energy. But, so what's it an increase in? Increased kinetic energy is reflected in the...
Movement.
Increased kinetic energy is increased movement.
Temperature.
Yes, you got it. The Man from Santander. I saw that movie. It was simply called The Man from Santander. El Hombre de Santander. El hombre o el hombre?
El
El hombre.
El hombre. Yo tengo hambre. Yo no tengo hombre. Por favor. Sí, yo tengo hambre. Es similar. Muy bien. Muy bien. So, its kinetic energy will be reflected in an increased temperature, right?
So if the temperature doesn't increase,
If the temperature doesn't increase,
kinetic energy is not increasing.
then kinetic energy is not increasing en punto. Muy bien. Perfecto. ¿Qué más? ¿Qué es eso? What is the energy change then? The energy, isn't energy going in? 540 kilocalories. What is the energy needed to change solid water, 0 degrees Celsius, to liquid water, 0 degrees Celsius? That's called heat of fusion, and it's 80 kilocalories per kilogram. But I want to know, where does the energy go? It takes so much more energy to convert liquid to gas than it does solid to liquid. 80 versus 540. More than 6 times, right? Yes?
Yes.
What happened to your pants? No, it's fine. It's fine. He's decent. There's modesty here. It just looks weird. But it's fine. He's fine. He's very modest. He has shorts on with a tie and shirt on. It just looks weird. It's like an Egyptian thing or
That's what it is.
creative. Excellent. I like that. God bless all Egyptians. Okay. So, now, so what are you increasing? What are you increasing? The level of what?
Calorie. Level of temperature.
Starts with a P.
Pressure.
Pressure.
Ends with a Y. 2 words.
High.
Pi, right? Right. PY, right? Potential energy, right? The potential energy is increasing, isn't it? Going from a liquid to a gas without a change in temperature, correct? All right, good. So let's talk about evaporation. Are we done? Did we talk about evaporation? We're actually going to be finished before we're finished because what I explained in the last class, it's difficult to treat this in a discrete manner, like only talk about kinetic energy without talking about anything else here. Why is it difficult to do?
Because it's all really.
Because you learned the material. You may have learned individual vocabulary words when you first started, but now what did you learn? You learned the connections among the vocabulary words. So I could explain to you kinetic energy from soup to nuts and use nearly every word on this board to do it. I could use any word on this board to define most of the words on the board. Isn't that weird? Weird, huh? Cool. Kinetic theory we talked about. Give me the different ideas of kinetic theory. Where's 10? Oh, 10's here. 11's up there. Let's talk about kinetic theory just for a second. What is kinetic theory? Do you have any things that, I mean, most theories you have this this list of criteria for it to be kinetic theory. Do we have anybody who has that list? Yes, Dylan.
What's kinetic theory?
Yes.
Matters
In constant motion. Consists of tiny particles that are in constant motion. Undergo what kind of collisions? Elastic collisions. Do the molecules in a gas undergo energy decreases according to the kinetic theory?
Yes.
They do?
No, they don't.
Kinetic theory of gases? No, they don't. Because the elastic collisions, where are the elastic collisions?
Top right corner. Top right.
Elastic collisions, define for me elastic collision.
Oh, collisions that come back to their original forms.
Measures how.
Yeah, come back to the original form, no deformation. Go ahead, we got a Connor down over here who's doing elastic collisions. Connor, he's from Australia.
When kinetic energy is transferred.
When kinetic energy is transferred without a loss of energy, that's an elastic collision.
One particle to another.
What is it?
From one particle to another.
From one particle to another. When energy is transferred from one particle to another without a change of energy, that's called an elastic collision. Right? Seems a little weird, like if it transferred energy, doesn't it have no energy, so it must have a loss of energy? But what's one of the things about kinetic energy?
It exchanges.
It exchanges, but some of this goes here and some of that goes there, right? This is going to lose half of its kinetic energy. This is going to lose half of its kinetic energy.
It's going to gain each other's height.
Gain, loss, gain, loss, gain, loss. Plus, what's happening instantaneously after this one may lose some energy, what's happening? It's going to get it back. You get this constant,
Elastic.
crazy group of these elastic collisions. Correct? Yes? Okay. Let's talk about some of this first for a moment. This is kind of, these are kind of unique. Because these talk about solids, you know. We've been talking a lot about gases and liquids. What's the study of gases and liquids called, generally?
Gas.
Anybody know? It's called what? I mean, we could spend an entire year on the study of gases and liquids. It's called chemistry. Close. The father of chemistry was involved in the study of gases. Boyle, the father of chemistry, yes. It's called fluid mechanics. Fluid mechanics is made of fluid statics and fluid dynamics. My favorite study of chemistry, fluid dynamics and mechanics. Fluid mechanics, fluid dynamics, fluid statics. Okay. But this is where we go with solid. What's a unit cell? Yes, we have a unit cell here. Yes, Alec.
Smallest group of particles in crystal has a geometric shape.
All right, we gotta speak up there. That was like, I didn't even hear that. Yes. The smallest unit, or the smallest grouping of a combination of elements within a crystal that reproduces a pattern which is obvious in a macroscopic example of the crystal. Was that cool?
There's 3 kinds as well.
There's what?
There are.
That was pretty good, I think. Yeah.
They have 3 here.
There's what?
There's 3 kinds.
3 kinds?
Isn't there?
I think, I don't know what that
I
means.
think, I
There were
think,
only 3 examples.
All right, okay, tell me.
There was simple cubic, body,
Simple cubic, I like that.
body centered.
Body-centered cubic. Give me an example of body-centered cubic. Is there one?
Yeah, it's like,
Sodium chloride?
oh, it doesn't give an example.
Doesn't give, I think.
But
What else? And then,
face
face-centered is sodium chloride, I think, right? Look that up. Sodium chloride, basic unit cell, look something, take out a iPad or something. Alec, don't you do that because you're telling us all about this.
okay.
So there's the simple cubic,
Yeah.
there's the face-centered cubic, and the body-centered cubic.
Yeah.
I think cesium chloride is body-centered. Somebody look up cesium chloride basic unit cell. Somebody look up sodium chloride basic unit cell. All right, what else you got for us, Alec? Alec is reporting from the field. He's in a crystal cave in West Virginia in the United States, and is reporting to us by telephone. We have him on speaker now. Carry on. Can you hear me, Alec?
Yeah.
Excellent. Yeah, he's there. Excellent. What else have you found out?
They're arranged in an imaginary cube, so they kind of form like a cube-ish form.
So say that once more.
The atoms or ions are arranged in a form.
The ions that make up the crystal, like sodium and chlorine, are arranged
in a cube form.
in a cubic form-ish. Yeah, because some of the cubes don't look like cubes. They may not have the same measurements of cubes. You're looking at literally it's like a geometry course. You're looking at the sides, the relationship among the sides, 3 dimensions, the sides, right? And then you're looking at the relationship among the angles, right? Correct? Yes? Good. Carry on, Alec.
And then body-centered is sort of like simple cubic, except it has at the center of the cube, there are atoms and rings as well.
Right. Yeah, you have body-centered. I'm terrible at, even though I've taught geometry, my idea of a geometric figure is a stick man. So this may be a little bit difficult. So let's see if I can do this. Here's a cube. So let's get rid of this. Okay. So there was body-centered. There's an actual ion completely in the center,
Yeah.
correct? And then there's something like 1/8 of the other atom
Yeah.
is around the cube based on the number of sides, right? Isn't that right?
That looks like it's right.
Yeah.
Based on the picture.
Can you show me that?
Just draw a circle on every corner.
And then there's like 2.
Yeah, I should get my Play-Doh out. Maybe I should get my Play-Doh out. I'll put this on pause and I'll get my Play-Doh out. Okay.
But it looks
Yeah, I see what you're saying. Excellent. Okay, good. All right, let me get my Play-Doh out and I'll show you. All right, in a minute. Okay, so what else you got for us? Is that it?
and then there's face-centered where it
So there's face-centered, right? Where there's a face in the side, like right here,
Yeah, and then on the other side.
and then on the other side. Excellent. Excellent. So that's like half of one, right?
They have an example here.
Yeah.
So
I think there's a full body, it should be full center body cubic because there's one of the ions is completely, absolutely, positively in that box, right?
Yeah.
And then the face-centered cubic is half of an atom is in the front, is in this, half fits in the back, and the other side, there's half in the box and half in the back. That makes 2 halves in a whole, right? Is that correct? The back of them. So they're, I have to bring my Play-Doh out. All right, what's next? Are we done, Alec?
Yeah, that was it.
Excellent. We did unit cell just now, right?
yeah.
Okay, what about crystal? We kind of defined crystal, didn't we?
Yeah.
What's the difference? What is a crystal? In one word, one sentence definition of a crystal. What does it say in the book? Somebody look up the word, just the basic everyday definition of a crystal. Dylan.
Particles arranged in an orderly repeating 3-dimensional pattern called a crystal lattice.
Oh my God. What did you just say? That sounded great. Was that out of the book? Wow, I thought you were being like incredibly articulate.
I am very.
You are. Can you come closer off camera and just read that to me again so I can? It sounded brilliant. Okay, say it again. Say it, you know what? Say it right here really loud. All right, this is Dylan. We have a guest appearance. Okay, we have in the studio with us today someone called Dylan. She's wonderful. Okay, read that in one breath. Go.
Particles arranged in an orderly, repeating three-dimensional pattern called a crystal lattice.
I love it. Okay, I love that. Now, so it's what's the difference between a amorphous solid and an amorphous solid?
Amorphous solid,
Amorphous.
solid, and amorphous solid is not solid.
No. That was good though. I like that. Yes.
Amorphous.
Amorphous solid is a crystal, something with a definite shape. Didn't you say that, Dylan? Let me read that myself. Tell me that. No. You tell me and I'll repeat what you say.
Particles arranged in an orderly,
Particles arranged in an orderly,
repeating
repeating,
three-dimensional
three-dimensional pattern. A lot of great adjectives there.
called a crystal lattice.
Called a crystal lattice. So that's amorphous. In other words, that's something with a structure. A solid with a definite, identifiable, I can put my finger on structure is amorphous solid. Why did I use the word amorphous? Because of the word amorphous.
In the box.
Amorphous means no structure. Amorphous is structure. Amorphous means without structure. So if you have an amorphous solid, you obviously can have a amorphous solid. Amorphous solid is a crystal, something with a simple, basic, repeating structure that gives rise to the macro obvious crystal, shape of the crystal. Very good. Nice assist. Do you understand that? So who has amorphous?
I do.
Who has it? Yes. What did I say? Did I have to add to amorphous? Go ahead. Read it right out of the book. What amorphous?
An amorphous solid lacks an ordered internal structure.
It just lacks an orderly internal structure. Isn't that what we just said? If a crystal glass isn't a crystal. You can make glass crystal-like by adding things to it. Yes? But that silicate, that silicon oxide, it's not very, especially the old stuff, it's not very crystal-like. It's considered an amorphous solid, right? All right, let's push on. We have 2:30. So allotropes is pretty easy. That's a good one. Allotropes is a good one. What are the famous three allotropes of a single element? Give me three allotropes of carbon. Diamond, graphite, and what?
Fullerene.
Fullerenes. And what's fullerene? What does that mean?
Oh, they're tube-like.
What are fullerenes?
It's when carbon's arranged in a tube, like.
Carbons arranged in a tube. Anybody else got that?
60 carbon
Looks like a
atoms.
soccer ball or a tube.
60 carbon atoms forming a hollow sphere.
Yeah. Yeah. And where did he get the tube thing from?
Probably graphite.
Yeah. Yeah, fullerenes. What are fullerenes?
Graphite is flat with lots of layers, though.
Right. Yeah, graphite has layers that are kind of not connected.
Fullerene is a hollow sphere.
Yeah, we're talking fullerenes are the balls, right? What's the name of those fullerenes? What's the name of where you have 60 carbons, C60? What are those called?
Buckminster Fullerene.
Yeah, Buckminster fullerenes, or otherwise known as simply buckyballs. C60. I have 60 carbons arranged in a sphere, invented or identified or produced by a fellow by the name of Buckminster. I think that's his last name, Buckminster. Is that right? Okay. And we call them buckyballs. Okay. But the two main ones, diamond and graphite, those are the two all-time famous ones. You have allotrops. A difference of an element based on the structure. Yes?
What were the tube-like structures?
I don't know.
I can't remember.
I'm not telling you. This isn't about me. today. This is about you, yes.
Isn't glass amorphous? or-
Yes, I said that. Glass is amorphous. Yeah, you can make glass crystal-like. What do you call crystallized glass?
Crystalline.
Crystal. Crystalline. Crystalline. But yeah, it's simply called crystal. Who makes some of the most famous crystal glass? In Waterford, Ireland, I spent 6 hours hitchhiking towards Cork, standing outside the Waterford Crystal plant. No one gave me a ride. I'll always remember Waterford Crystal, always. Now, so good. We're cool with that. So let's do. We did this. We did this. We didn't do this. Normal boiling point is simply what? What's normal boiling point?
Is the boiling point of a liquid
100.
at standard, 1
STP?
atmosphere. Yeah, 1 atmosphere. Doesn't talk about pressure.
It should 100.
Or 1.3.
Yeah, but standard STP is what?
Standard.
Standard temperature and pressure. And what are the standard temperatures and pressures?
0 degrees Celsius and 1 atmosphere.
0 degrees Celsius. And what's normal? What's NTP?
30 degrees Celsius and 1 atmosphere.
Well, I'm not sure it's 30 degrees Celsius, but it doesn't matter. I very rarely use it, but it's. I mean, you do use it in a lab, but it's normal. Room temperature. Room temperature and pressure at room temperature. Okay, now. So. Barometer. Let me tell you a story about barometers. When I was a relatively new science teacher back in the late 70s, early 80s, and even until the late 80s, I guess, we would do chemistry labs, yeah, and when we did gas laws or chemistry experiments that were pressure sensitive, such as equilibrium labs, gas pressure labs, gas law labs, right? Anything with a gas, really, anything with density. You had to take down the pressure in the classroom. And every classroom had a barometer in it. Very expensive barometers. And these barometers were more than a meter long. They're like this. And the tube was like this long, this big. Pretty serious tube, right? It was more than a centimeter. And it was completely filled with mercury, liquid. That wasn't sealed. It was in it was sealed, I suppose, but it was upside down in a pool of mercury. Here's the mercury here. The open tube is here. And it was upside down tube. You could easily take the tube out if you wanted to. And it was in a tub of mercury, okay? And what you did was, if you take a tube of mercury, okay, here's my tube. You can't see it, but you can pretend it's there, right? And it's open on one end and closed on the other, right? And you take the tube and you put it in a big vat of mercury. You take your finger and you stop it, right? Then you take it and you keep your finger in the bottom of it and you take it and you put it upside down so that the liquid, so that the opening is in the mercury. And then you take your finger away and the mercury will drop a little bit, right? And the height between the mercury pool and the top of the column will be 760 millimeters, 0.76 centimeters, correct? And the pressure of the atmosphere is going to be 101 kilopascals, and we know what SI pressure is. It's going to be newtons per square meter, right? That's 1 Pascal. And the atmospheric pressure pushing down on that liquid that drives the mercury up the tube is called regular atmospheric pressure. And then you would adjust it and find the tip of the mercury, and you would take this little slide bar and then you slide it to where the tip of the mercury is, and then you read it. And if it's exactly 1 atmosphere, you would read 760. If it's high pressure that day, it might be 765 or 767. If it's really low pressure, a storm's coming, it would be 750, depending upon the atmospheric pressure.
Is it okay to dip your hand in mercury?
I would not recommend going anywhere near mercury.
What about like the
Well, I know that because that's the way we did it. It was just so weird. The barometers we used back in the day with students, it was terrible. In our laboratory in college, we used to work with mercury, and we were on our floor we had these boards that we would walk on with slats in them. And then the mercury would fall into the boards and go between the boards. And then at the end of the day, we would take sulfur powder and take the sulfur powder and throw it on the boards on the floor. And the mercury would bind with the sulfur and become non-reactive. And then they just sweep it up and throw it away.
Is that
Weird.
what mercury is?
Weird. But the dangerous mercury is when mercury is ionized. If it's in a gaseous state or it's ionized. Mercuric chloride. If somebody says to you that they have mercuric chloride and do you want to see it, you know what you say?
Run.
No. You might want to run. You might want to pick new friends. But but mercury is not, you've heard of something called the Mad Hatters?
Yes.
You know, well, in felt making, we're not going to talk about felt making today, but we will. But the making of felt hats, they use boiling water now, but they used to use mercury salts and rub it in, and it does terrible things to your nervous system.
Why is the mercury in thermometers red?
That's not mercury, that's alcohol. Red thermometers are alcohol thermometers. Yeah, that's not mercury. If the thermometer's red, say, thank you very much. If the thermometer is silver,
Great.
say, goodbye. Okay. So you have a question, Enzo.
Oh, well, I just wanted to point out that the Mad Hatter from
Alice in Wonderland.
Alice in Wonderland.
Based on
Yeah.
the Mad Hatter.
In the 19th century, that's what they used. They used mercury salts, yeah. And we'll talk about how, all right, shall I tell you? All right, you can use wool to make clothing, and you form it into thread and to yarn, and you can make clothing, knitting it, etc., right? Crocheting, knitting, put it on a loom, wool pants, whatever the case may be, right? You're weaving it so it holds together. Well, years ago, what they used to do is they used to not go through the looming process or the darning, whatever you want to call it. They would simply press it, and they would take the wool and press it, and it would stick together, and it would stay pressed together. You couldn't get it. It was a matting. Anybody have a dog in here?
Yeah.
Well, the matting that happens behind the ears of the dog, same idea, where it's matting, right? And the reason it mats is because here's a wool strain, right? Well, if you take it and nick it, just nick it. You're just nicking it. You're just putting a little nick in it, right? Like a wire, you just nick it, you know? So you put thousands of nicks in these strands of wool, and then what's going to happen? The nicks line up and they bite into each other. So you get it that it sticks together. Now the way you nick it is to use mercury salts or boiling water. The Mongols used to do it. They used to sit on it and ride for long periods of time. They would put it under their saddle, and that's how they would make this material. We call it felts. It's called, you ready? Felting.
Scientific.
Yeah, and that's how they did it. They put nicks in the wool, and the wool would stick together.
But
They
why
mix-
mercury salts? Why not any other?
It's just the way, that's what they used. Why? How does mercury salts work more than? I don't know. It's a good question. Why don't you look that up? Okay, clear? Okay. Do you have your homework today? No. Okay. Enzo And Alex, see me after class. Okay, good. All right, so let's continue. Dynamic equilibrium is what?
In a system at constant vapor pressure.
In a system at constant vapor pressure, like room temperature, like in a room,
A dynamic equilibrium exists between the vapor and the liquid.
between a vapor and a liquid. In other words, I take a bottle, right? It's half full. I put the cap on. What's going to happen? Water's going to evaporate, cool, go back in the water, evaporate, cool, 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 back in the water, back in the water, right? And that's called a dynamic equilibrium. When it keeps exchanging vapor